All right, so chapter 15, what we're going to be looking at is chemical equilibrium. And when we're looking at chemical equilibrium, um, what we're going to see is that with these reactions, when they're at equilibrium, what that's going to mean is that the forward reaction is going to be occurring at the same rate as the reverse reaction. So typically, we kind of only think about reactions going in one direction. So in this case, we could take the N2O4, convert it into NO2. So that's why we're starting to get that orange kind of brown color being produced, is because we're starting with just the N2O4, having it convert into NO2. But what we're going to see with certain reactions is rather than just having the conversion of N2O4 into NO2, what we're going to see at the same time is some of that NO2 is going to get converted back into the original N2O4. And when we're looking at chemical equilibrium in particular, what we're going to see is the rates of those two reactions when we're at equilibrium are going to be equal. So if you look at the graph here, initially we start with a fast, so they're using, just like the last chapter, K, little k is referring to the rate of these reactions. So F is looking at the forward reaction, R looking at the reverse. So initially the forward reaction is proceeding at some rate, and then as we start to produce some of the product there, now we start to see the reverse reaction start to get going as well, start to speed up while the forward reaction slows down. And eventually we hit a point where both of those reactions are going to be equal. That's going to be what we're considering equilibrium to be. So the forward rate and the reverse rate are going to be the same speeds. With that though, and one it's often one of the things that trips people up the most is when those rates are equal. If we were to kind of stop and look at the reaction, it would look like nothing was actually changing, because when we get to this point, we can see in this case, rather than rate, we're looking at concentration. But when we get to that equilibrium point, now that we're having the forward and the reverse rates occur at the same rate, it's going to look like nothing's actually changing. So that's why at equilibrium, when the rates are equal, the amounts of these substances are going to be constant. So if we go back for a second, the rate one again, equal rates, meaning we're taking just as much of this NO2, converting it back to N2O4, as we're taking the N2O4, converting it into NO2. And that's why when we do get to that equilibrium point, we see that these amounts stay constant, but they're not going to be equal. It could potentially be equal, but for the most part, we're going to have more of the reactants or more of the products. We're going to have more of one of those substances, or more of one side of the reaction than we will the other. So this is often going to be the case. In this case, what we're considering the product, we wind up with more of. Doesn't necessarily have to be that way, but we will generally see that these amounts are going to be different. But at equilibrium, since the rates are going to be constant, or the rates are going to be equal, that's why we see these amounts or these concentrations staying constant here. And then with the reaction itself, when we write the chemical equation, typically when we look at these equations, we've only seen them go in one direction, so we just have that one directional arrow. But when we're looking at reversible reactions, so reactions that can go in both directions, that's going to be when we're using the double arrow, and specifically when it's at equilibrium, because now we're representing both of those rates are going to be equal. But with this, just recognize not every reaction is going to be reversible. So if we think about a combustion reaction, for instance, if we burn something, we can't unburn it. We're not going to have some of the carbon dioxide in the water, whatever we're producing there. We're not going to have it get converted back into the original hydrocarbon or whatever it was. So with this chemical equilibrium, it's going to be not something we see with every reaction. But with that double arrow, if we're looking at the forward reaction, so if we go back for a second, the way we have it here, N2O4 is on the left, NO2 is on the right. So with the forward reaction, we're taking this N2O4, converting it into NO2, and we're going to consider that to be the forward reaction, just because that's the way we typically would read the chemical equation. And then with the reverse reaction, then we're just going in the opposite direction. So that's why in this case, we can see we're kind of just switching these two around. And then thinking about the rate laws that we wrote in the previous chapter. we can see it's pretty much the exact same thing there. So the rate of this forward reaction is going to be equal to that rate constant times the initial concentration of N2O4, just because we have a coefficient of 1 there, while the reverse rate is going to be equal to the reverse rate constant times the square of that NO2 concentration, because now we've got a 2 in front of it. But like I said, at equilibrium, those two rates are going to be equal, so we can set them equal to one another. And then we can further rearrange this so that we have the concentrations on the same side and the rate constants on the same side as well. And the reason we're going to do this is because when we're looking at these equilibrium, or these reactions at equilibrium, we're going to have the equilibrium constant, which is going to allow us to determine what the concentrations of these substances are at equilibrium. And remember, with the rate constant, from the previous chapter, those rate constants were temperature dependent. So as we speed up, or as we increase the temperature, a lot of the times we see the rate increase because the rate constant itself is going to be temperature dependent. So we're going to see the same thing with these equilibrium constants. So with the equilibrium constant, you can see we're just going to have the concentration of these two substances. And with it, in general, the way we're going to be able to write these is by essentially just taking the concentration of the products, raising them to whatever coefficient they have. So in this case, the capital letters are referring or are representing our substances, and then the lowercase ones are representing the coefficients here. So that's why we've got the concentration of C raised to C power. Same thing with D, A, and B. But with this one, we're going to have products in the numerator. We're going to have our reactants in the denominator. So that's why we've got C and D on top here, A and B on the bottom. So with this, if you want to take a second just to kind of go through and see if you can write the equilibrium constants, or the equilibrium expression, I should say. So where we're actually kind of taking the concentrations, raising them to the correct coefficient. So see if you can do that for these three reactions here. And with it, so if you want to give yourself a chance to go through that, write these on your own, definitely just go ahead and pause the video. But I'm just going to go ahead and show the answers for these ones. But remember, it's just going to be products over reactants, and then we're going to raise the concentration of these substances to whatever coefficient they may have. So with the first one, whoops, looks like the arrow on this one just got a little messed up there. But since O2, that the diatomic oxygen, is going to be our product, ozone is our reactant, we're going to have O2 on top, ozone on the bottom, and then we're going to raise them to the coefficients. So since we've got a 3 in front of oxygen, we raise the numerator to the third power, while we're just going to square the ozone in the denominator. And then kind of the same thing with these bottom two. Again, products on the top, reactants on the bottom. So that's why we've got NO and chlorine, ammonia, and that silver ion on the bottom there. And then we're just raising these to the coefficient. So we've got 2s on a couple of them, 1 for these chlorine, just because it's a coefficient of 1. And then kind of the same idea at the bottom here. So the only reaction, or the only substance in this third one that has a coefficient in the balanced chemical equation is going to be ammonia. So that's why that's the only substance that we're actually raising to some power here. And then with these second and the third ones, just note that the denominator, I just put it in the parentheses there because we're going to multiply these together and then divide the numerator by that entire product there. And I'm using product in the sense of the answer to a multiplication rather than the reaction. And then with these equilibrium expressions, so we've got Kc, the C is referring to concentration. We can represent a very similar idea when we're looking at reactions that are all gases. We can do that by using the partial pressures. So in this case, instead of Kc, we've got Kp, because we're looking at the pressure of these substances. Still kind of the same format for this reaction, and again, the arrow seems to got misplaced for some reason. But with it, we're going to be looking at the partial pressures, because with this reaction, they're going to be in the same volume. So the amounts of these the pressure of these substances is going to be directly related to the moles. So again, C and D are our products, A and B are our reactants. So we're going to take the partial pressure of those substances, still have products on top, reactants on the bottom, and we're still going to raise them to the coefficient in the chemical equation. A very similar idea. It's just instead of using the concentration, so instead of using molarity, we can use with the gases, we can use the partial pressure as a substitute. And then with Kc and Kp, we're going to actually be able to relate those two together. So if we think about the ideal gas law, PV is equal to nRT, we can rearrange that just to solve for pressure. So divide both sides by volume, we get nRT over V. And what we're going to be able to do then is use this equation to relate Kc and Kp. So if we already know what Kc is, we can calculate what the equilibrium expression is going to be in terms of the partial pressure of those different substances. And then R is still going to be our gas constant. T is still going to be temperature in Kelvin. And then this delta N is just going to be the change in moles. And we're looking at the change in moles of gases. So it's going to be the moles of gas product minus the moles of gas reactant. And if you think about it, if we have the same number of moles on each side of that reaction, so if we had 2 moles on the left, 2 moles on the right, we're going to have 2 minus 2. That delta N is going to be 0. So in the case where there's equal moles of gas on both sides, Kc and Kp are going to be equal to one another. But just so we can kind of see where this equation comes from, if you look at the top here, in this case, they kind of just took that ideal gas law that we just rearranged, and then we're just specifying this is going to be for substance A. So that's why we've got partial pressure of A, moles of A. And if we've got moles over volume, that's really just concentration. So the partial pressure of that gas is going to be equal to the concentration times the gas constant times the temperature. So now if we look at our equilibrium expression in terms of the pressure, we can take the partial pressure, and we're just looking at D here, but we can do the same thing for E, A, and B, any of these substances. We can take this and substitute in for the partial pressure. So we can take the concentration times the gas constant times temperature, substitute it in for the partial pressure of all of these substances. And we get this very similar equation at the bottom here. And with it, we've got the concentration RT for all of these substances, and of course raised to the coefficient. So what we can then do is essentially remove the RT piece of it. And now when we look at what we have rearranged here, so we've still got to have this coefficient go to each of these pieces. So we're separating out the concentration and RT, but that exponent is still going to go to both of them. So that's why when we're looking at the concentration here, we still have concentration of A, B, D, and E raised to that coefficient. But now for the other term, the RT that we've removed from both the numerator and the denominator, in the top, RT is being raised to the power of D, same thing with E. And then on the bottom, we have the exact same thing occurring with A and B. So that's why we can kind of rearrange it as we see here. And then if we look at what's in the parentheses now, this is just going to be our equilibrium expression in terms of concentration. So this is just going to be Kc, because we've got the concentration of all of these substances raised to the power. So we can substitute in Kc for this, and we can essentially just combine this RT fraction piece into one term. So with the exponents, remember, if we're dividing exponents, it's really the same thing as subtracting. So we can have RT raised to the D plus E minus A plus B power. And that's just how we get the delta N there, because that's going to show us the change in moles of gas of these substances. So then using that equation, the relationship between Kc and Kp, if we're given a reaction like this, so the Haber process, the production of ammonia from elemental nitrogen and hydrogen, we're given the equilibrium constant for Kc, 9.6. And again, this is going to be temperature dependent. So that's going to be for 300 degrees C. We want to calculate what Kp is. And with this one, we can just go back, use that equation, because if we think about it now, we were given Kc. R is just going to be the gas constant, so we always have that. P is just going to be the temperature in Kelvin, so we were told 300 Kelvin, or 300 degrees Celsius, rather. So we're just going to want to convert that to Kelvin, 573.15. And then with the delta N piece, all three of these substances are gases. We've got 4 moles on the left, only 2 moles on the right. And with delta anything, it's going to be final minus initial. So in this case, products minus reactants. So it's going to be 2 minus 4. We'll have -2. So when we go through, oops, and that's actually the incorrect number there. So let me double check because I think this is actually wrong. But this should be -2 here because we've got 2 moles on the right, but 4 moles on the left. So I'm guessing this should really be 2.12 maybe, but let me just double check that quick. I got the calculator right here. So 0.08206 times 573.15. Square that. Whoops. But when I squared it again, I did the same exact mistake. Oh, very different. Yeah, so that is incorrect. So we will fix that right now. So we should have 0.0443, and then with sig figs, we've got 3 of them in the equilibrium constant given. So we'll keep 3 of them in the equilibrium constant that we're solving for. So hopefully that is the correct answer. Let's just double check one more time. It's 573.15 raised to the -2. Oh, perfect. So now we fix that. And then again, with this, it really should just be, whoops, guys are not going to let me do the exponent there. All right, so fix that one. And then with this equilibrium constant, while I'm just getting this back to what it should be, with the equilibrium constant, just notice that there's going to be no units on this. So Kc, we weren't given units. Same thing with Kp at the end. So these equilibrium constants are going to be unitless. And again, I don't know why some of these double arrows keep getting pushed down a little bit. But when we're looking at equilibrium, again, we're going to get to the point where the rates of the forward and the reverse reactions are equal, which means the concentration of those substances are going to be constant. And then the equilibrium constant is going to be temperature dependent. So when we look at the table here, what it's showing us is that the way we get to equilibrium can kind of be reached in either way. So we can have a lot of one of these substances, a little of the other, or vice versa. And then no matter what, we're going to have equal, or essentially equal, values for the equilibrium constant. So if we look at trials 1 through 3, we've got none of the N2O4 to start, some of the NO2, whereas trial 4 is the reverse, the complete opposite. We've got N2O4, but none of that NO2. And in each case, when we get to the equilibrium, we'll see that the concentrations are different, but the ratio of those two is going to be the same. So the equilibrium constant is going to be equal. And then with 3 and 4, if we look at it, so since NO2 is really going to have a coefficient of 2, when we've got 0.04 of that and 0 of the other, or 0.02 of the NO2O4 and 0 of the NO2, we're going to see that they'll actually wind up with exactly the same concentrations there. But the important piece here is just to recognize at equilibrium, at a given temperature for a reaction, the equilibrium constant itself is always going to be the same. So the ratio of those substances is always going to be the same at equilibrium. So we can see all the way up till whatever time this is going to be. Of course, we've got different concentrations. We'll have different ratios of those substances just because we won't be at equilibrium. But once we actually do achieve that equilibrium, we've got the rates of those reactions being the same. That equilibrium constant at a given temperature is always going to be the same for a single reaction. And then if we think about K, what that represents, the value of K actually tells us the relative ratio of products to reactants. So when we've got a large K, if you think about the constant itself, the expression, we've got products over reactants. So if we've got a value much greater than 1, that means our numerator is going to be much, much larger. So with K values greater than 1, we're going to call them product favored, just because we're going to have more of that product present at equilibrium. Whereas the reverse case, they're going to be reactant favored, because if we've got a K much less than 1, that means our denominator is going to be larger, and that's going to be where we have the reactants. So with K, the value of it tells us which side of our reaction is going to be favored. Large K values favor the products, small K values favor the reactants. And when we're looking at these reactions, we've got forward and reverse, but that's kind of arbitrary, because if we look at these two, we can have N2O4 on the left, or we could put it on the right there. So calling it the forward and the reverse reaction is kind of specific to the equation that we're looking at and how exactly it's written. But with the equilibrium constant for those forward and reverse rates, forward and reverse reactions, excuse me, what we're going to see is that those are going to be the inverse of each other, essentially. So for the top reaction here, where we're going to be creating, or we're considering NO2 as our product, we've got the equilibrium expression shown here. And then that at 100 degrees, that equilibrium constant is going to be equal to 2.12, or 0.212, excuse me. So if we flip this reaction around, now when we write the equilibrium constant, we're essentially going to flip that as well. So now we've got N2O4 on top, NO2 squared on the bottom. So the equilibrium constant would get flipped as well. If you want to even think about this top one as 0.212 over 1. When we flip it then, that's why we get 1 over 0.212, or that's really going to be 4.72. And then with these equilibrium constants, if you think about it, one of these reactions, Lily, geez, write it down. One of these reactions, well, stop being a baby. Oh, yeah. So with the top reaction, for instance, this would be a small K value, meaning that the reactants are going to be favored. So it makes sense when we flip this around. Now we get a K value greater than 1, because we're still going to be favoring N2O4. But now that we've got that as our product, we've got it on the top of our fraction here, we should wind up with a larger value. So it makes sense that one of these is going to be a decimal. Or I guess they're both decimals, but one of them is going to be less than 1. The other is going to be greater. And again, this is going to be because they're at the same temperature. If we had this second reaction where we flipped it at a different temperature, we wouldn't be able to just take the inverse of the rate constant, or the equilibrium constant, excuse me. And then with these reactions as well, if we multiply them by some coefficient, so in the top one, we're still looking at that same reaction, still got the equilibrium constant of 0.212. But now if we take this reaction and double it, so we're changing the coefficients to 2 and 4, what we're going to see is that the coefficients in that reaction change as well. But what we're really going to be doing is just taking that equilibrium constant and raising it to the power that we multiplied the reaction by. So since we doubled the reaction here, we're going to be raising the equilibrium constant just to the power of 2. If we tripled the reaction, we'd raise it to the third power. If we cut a reaction in half, We could take the square root or raise it to 1/2 power. But it's just essentially taking whatever that multiplying factor is going to be and use that as the exponent on those rate, the equilibrium constant. All right, so if we look at or if we think about a reaction that's going to have multiple steps, what we're going to see is that the equilibrium constant is just going to be taking those, the equilibrium constant for the entire process, I should say, is going to be equal to the product, so multiplying the equilibrium constant for the individual steps. So if we look at so with this one, just looking at the inverse essentially, because we're going to be flipping this one. So we're told that the Kc for this bottom reaction here, I guess I'm already showing you the answer. But with the bottom one, we're told the equilibrium constant is going to be 1 times 10 to the negative 30 when we're taking nitrogen and oxygen, converting them to NO. And this is going to be for 25 degrees C. So if we want to get the equilibrium constant for the reversed reaction, so if we flip that around, what's the equilibrium constant going to be? What we can do is just take the inverse of that. So we'll have 1 over 1 times 10 to the negative 30th, which is really just going to give us 1 times 10 to the positive 30th there. So with the flipping of these reactions, the equilibrium constant is just going to be the inverse. But now with this one, we'll be able to see the sort of that step process I was referring to. So if we've got multiple steps, the equilibrium constant for the overall process is just going to be the product of those steps. So with this one, if we look at it, what we're going to have to do is, and this is going to be kind of similar to Hess's law almost in this case, because if we look at it, we've got HF in one spot in the reaction, the steps that we're given. But in the steps, got a coefficient of 1. Here it's got a coefficient of 2. And then with the second one, if we look at the H2C2O4, we can see we want that as a product, but it's listed as a reactant in the step. So we're going to have to multiply the reaction on the top by 2, which is going to mean we're going to have to square this equilibrium constant. And then we'll have to flip this reaction around, which means we'll have to take the inverse of the second. So with this, since we're going to try to squeeze a 2 in there, didn't really work too well. That means we're going to take this equilibrium constant and just square it. And then with this one, since we're flipping everything around, we're going to take the inverse of it. So I'll do something like this. So again, and then if we were to actually add these reactions up, what we're going to see is 2HF is only in one spot, so we'll wind up with that there. We'll flip this around, so we'll wind up with C2O4, that oxalate ion, as a reactant. The oxalic acid is going to become a product. Same thing, the F stays on the right-hand side. And then with these 2 hydrogens, since we flipped this bottom reaction around, we've got 2H plus on the right of the first one, 2H plus on the left of the second one. So those are just going to cancel. But with this, when we take the equilibrium constant now and then actually multiply those together, so we'll have 6.8 times 10 to the negative 4th. And then we'll square that one. Oops. So negative 4 squared. And then we'll have the inverse of 3.8 times 10 to the negative 6th. And when you multiply those two together, what we should get is going to be Kc will be equal to 0. And then how many sig figs do we want? We got 2 in there, so we'll keep 2. 0.12. And again, all I did was square this first one. Since we multiplied it by 2, we're going to raise it to that power, so square it. And then with the second one, we just took the inverse around. And with these, you can always double check just to kind of make sure that the exponents are going to be correct, because really what we're doing here, if we wanted to, we could kind of show our calculation as this, because multiplying by the inverse is really just the same as dividing by the original value. So we could have 6.8 times 10 to the negative 4 squared on top. We'll have this on the bottom just as the original number, which is the same as multiplying by the inverse. So if we look at the exponents, negative 4 squared, really going to give us negative 8 on top, minus a negative 6. So we'll have negative 2 as the exponent. And then that's always plus or minus 1, because depending on the numbers themselves. So we really wind up with 1.2 times 10 to the negative 1. So it's a pretty good chance that we're at the right spot. So you can always just double check, make sure you're in the right ballpark, by just doing a little quick math with just the exponents we have there. And then with that equilibrium constant, if we think about it, 0.12, it's a value less than 1, which means we're going to be favoring, oops, I got it really bad. We're going to be favoring the reactants here, just because our numerator is going to be larger in that case. And then with these equilibrium constants, when we're writing those expressions, what we're going to be doing is only paying attention to aqueous or to solutions. So typically going to be aqueous, because for the most part we just dissolve stuff in water. But we're going to be paying attention to solutions, and we're going to be paying attention to gases as well. But solids and liquids, we can essentially just remove them from our equilibrium constant, because the concentration of those is always going to be constant. And the reason for that is the density and the molar mass at a given temperature. The molar mass is always going to be the same for a substance, but the density at a given temperature is going to be the same. So the concentration isn't actually going to change at all. So if you think about just a piece of paper, for instance, it's got some mass, it takes up some volume. If we cut it in half, now we've got 2 smaller pieces, but the concentration would essentially be the same, because the mass is going to decrease, going to get cut in half, but so will the amount of space it takes up. And that's going to be a similar idea with pure liquids as well. We've got a cup of pure water. It's going to have some concentration. If I then pour half of that cup out, we've decreased the amount of that substance by half, but we've also decreased the amount of space it takes up by half. So the concentration isn't actually going to change. So when we're looking at writing equilibrium expressions for reactions that contain solids or liquids, we're just going to ignore them. So if we look at the reaction here, so it's going to be the dissolution of lead 2 chloride into just the lead 2 ion and the chloride ions. So when we write the equilibrium expression, we'll treat the right-hand side, we'll treat those products the same, because both of those are aqueous ions. So Pb2 plus, and then we'll square the concentration of those chloride ions. But since the original lead 2 chloride is going to be a solid, we're not going to include that in our equilibrium expression. So in this case, the equilibrium constant is only going to be dependent on the lead ions and the chloride ions. But the original lead chloride, it's lead 2 chloride itself, won't affect it at all. And we can see something similar here. So in this case, it's going to be the decomposition of calcium carbonate into carbon dioxide and calcium oxide. So if we were to write the equilibrium expression here, it would simply just be the concentration of that carbon dioxide. And what we're going to see is, as long as there's some of the calcium carbonate or calcium oxide that's solid, as long as some of that remains in the container or wherever this equilibrium is being reached, we're going to see that there's always going to be some amount of the there's always going to be that same amount of carbon dioxide present. So with it, if we think about it, we're going to ultimately see with later in this chapter, we can sort of affect this equilibrium. We can push it one way or the other. But we're going to see that the addition of solid just won't affect the equilibrium at all, won't affect the concentration of that carbon dioxide. All right, so with these ones, so with the two here, if you want to take a second just to write the equilibrium expression for both of these reactions. And again, we want to just pay attention to the solutions or the gases. So in this case, we can essentially remove the liquid water from our first one. So we write the equilibrium constant Kc. On the top, we'll have the concentration of carbon monoxide, and then we're not going to raise that to any power because all of these substances in reaction A just have a coefficient of 1. And then on the bottom, we'll look at the reactants, and since both of those are gases, we'll include the concentration of CO2 as well as the concentration of the hydrogen. And then with the second one, kind of the same idea, but we don't need to focus on either of the tin substances, so tin 4 oxide or just elemental tin. So when we write the equilibrium constant for or the equilibrium expression, I should say, for the second one, it's going to be the same idea, product over reactant, so CO2 on the top. And then now that this has a coefficient, we'll raise it to that power, so we'll square it. And then we'll do the exact same thing for the carbon monoxide on the bottom, since it's a reactant. Also has a coefficient of 2, so we'll also square that concentration as well. So with these equilibrium expressions, again, products over reactants, raise it to the coefficient, but we're only going to focus on gases or solutions. So since the water was a pure liquid, both of these tin substances are solid, we're not going to include any of those in our equilibrium expressions. All right. And then with the question here, we're told that a mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at 472 degrees Celsius. The equilibrium mixture of the gases was analyzed and found to contain the partial pressures listed there. From this data, calculate the equilibrium constant for Kp. So with this one, we're looking at the partial pressures, so we're given those in the question itself. So we really don't have to do too much work here, but we've got to think about how we're going to write that equilibrium constant. And in this case, since they're all gases, we're going to include all 3 of these substances in our equilibrium constant. So we'll have the concentrate or the partial pressure of ammonia, and then we'll square it on top. So that's why we've got 0.166 squared. And then the reactants on the bottom, N2, this has a coefficient of 1, so we don't need to raise that to any power. So just 2.46. But the hydrogen has 3 in front of it, so we'll raise it to the third power. 7.38 for the partial pressure of the hydrogen. And we're going to get a pretty small negative number here, 2.79 times 10 to the -5th. And again, that kind of makes sense because we've got 0.166 squared, so it's going to be a really small number. And then on the bottom, we've got 2 whole numbers, and one of them we're really multiplying by itself a couple times. So we should have a small number over a large number, so it makes sense that we get a small scientific notation, something to the -5th here. All right, and then the next one here, we're looking for the equilibrium constant in terms of concentration. So for this one, what we want to just recognize is concentration, molarity, moles over liter. We're giving you the moles directly. We're giving you the volume of this flask. So we just want to make sure that we um, account for the volume here. So we're going to divide all of these moles just by 2 because that's the volume of the flask in liters. So when you go to write the equilibrium expression, we'll have H2S squared on top, H2 squared on the bottom, S2 just as itself on the bottom. So when we plug everything in, we'll have on the top 4.35 squared because we're going to cut that molarity in, or we're going to cut that number of moles in half. And then on the bottom, we'll have 1.25 squared for the hydrogen, 1.35 times 10 to the negative fifth. We'll cut that in half and multiply it by 6.25 because that's what or actually it's not, that would be 1.25 squared. So we'll multiply the hydrogen squared times the S2 under the bottom, and ultimately that'll give us an equilibrium expression or equilibrium constant of 1.79 times 10 to the sixth. And with it, that's a really large number, which tells us that at equilibrium, at this whatever temperature this is at, because it doesn't give us any the question, but whatever temperature this equilibrium was reached at, since we've got a very large equilibrium constant, that means we're going to favor the products. So we're going to have a lot more of the H2S than we will the either of the reactants. And if we look back to the question, that's exactly what we have. We have 8.7 moles of the H2S, 2.5 moles of hydrogen, and then a very little amount of the S2. And then with it, that'll be where we wrap it up for this video, because we'll start to see with the next type of questions related to equilibrium. We'll kind of have to do a little bit of a table, what's known as an ICE table. But we'll see that in the next one.